Yeah. Hello, and once again, welcome to celebrate the National Periodic Table Day. Today, yes, today, 8th of February, which is the birthday of Dmitry Mendeleev. And in the first session, I had discussed about how to draw the periodic table and all the elements through song. And I discussed also the groups, the periods, the liquid elements, the solid elements, the metals, non-metals, metalloids, radioactive elements, synthetic elements, and all that we discussed. And also isotopes, all these aspects. Today, my colleague, Dr. B. N. Das, he will be discussing the important periodic properties, how they vary across periods, along groups. Over to Dr. B. N. Das.
Thank you, sir.
Hello, those who are watching directly from the YouTube. You listen to my colleague, Dr. B. N. Das. He was ex-professor of chemistry and also principal of a college, a degree college, SA Mahavidyalaya, Balipatna, Khurdha, and he will be addressing.
Thank you, sir.
Bye.
Good evening, everybody. I welcome you to the second session of the celebration of Periodic Table Day or the Mendeleev's birthday. Happy birthday, Mendeleev sir. Wherever you are, our best regards and wishes to you. And also, I am very much thankful to Dr. Tripathy, my teacher, my mentor, for giving me a chance to discuss something with the listeners. So let us start the variation of periodic properties in this discussion.
Sure.
So, let us start the periodicity in properties in the periodic table. Sir.
Steve, are you able to hear?
Yes, sir.
Are you able to see us?
Yes, sir.
Okay, just
Okay. So,
now you can, yes, participants. You can see the participants, right? See this there. What has happened? I don't know. 80. Oh, see, somewhere it is there. It is yours. 80 right? Okay. You are able to see, Siddharth?
Yes, sir.
okay. So,
80 SO,
sir, when we are going to discuss about the periodicity and properties of different elements in the along the periodic table or down the group, along the period and down the group, we will be discussing about the variation of atomic size, ionic radii, ionization energy or ionization enthalpy, electron gain enthalpy or electron affinity, or two terms are used in this purpose, electronegativity melting point, boiling point, density, enthalpy of fusion, enthalpy of vaporization, enthalpy of atomization. I have written ATM dot, VAP dot, or FUS dot, that is fusion, vaporization, and atomization, etc. Many properties are there. And while we are discussing about chemical properties, they include oxidation states and their variation, anomalous behavior of the second period elements, that is, the first element of second period differs in properties with the rest of the elements in its own group, but shows similarity with the element which is diagonally present with it. That is called the diagonal relationship. The character of the hydrides of the elements, oxides of the elements, halides of the elements, different elements, and their complex forming ability of different elements, etc. So my point is, why we are doing all these things? So the veteran chemists like Lothar Meyer, van der Waal, Mendeleev, Mosley, they have taken a lot of pain to prepare a table for us, listing all the elements in a very systematic manner based on atomic number. Chronicle development is there from atomic mass gradually, from Newland's law of octave, then atomic mass, then atomic number by Mosley. They take a lot of that. They took a lot of pain in arranging the elements in a proper order so that we don't have to remember them. We don't have to take a lot of pain in analyzing similar elements in a series or in a group so that we can remember them correctly. We can assimilate their behavior, we can analyze their behavior, and it will be radically easier for us to study the elements and their properties. This universe is made up of elements, matter, made of elements, made up of elements. So 118 elements are there, and you have already discussed, Sir has discussed everything in the first session regarding the different type of elements present in the periodic table. So my point is to focus on variation of some of the properties, physical as well as chemical, as per the time permit. So the first point is that, let me discuss about the atomic size and ionic radii. If you concentrate on the slide I have shown you, the first point I have written that it is difficult to measure the size of an atom in comparison to the measurement of size of a cricket ball. If we ask why this is possible, why this happens, why cannot we measure the size of an atom? Cricket ball is a macro object, a big object, and we can hold it, we can measure its radius, applying formula and all that. But when we are talking of an atom, it is very difficult to determine the radius of an atom, that is the distance between the nucleus and the valence electron. That will give you the radius of the atom. And we know that electron cloud surrounding the atoms does not have a sharp boundary because they are revolving at a tremendous speed around the nucleus in external orbit. And the electrons are extremely small, the atom is extremely small in size of an approximate order. I am repeating, approximator, we approximate. We cannot exactly calculate. So approximate radius of the order of 1.2 angstrom units. That is 1.2 into 10 to the power minus 10 meters. Such a small quantity. It is very difficult to have a measurement up to this dimension. It can only be determined by X-ray analysis and scanning electron microscopy, transmission electron microscopy, that is SEM and TEM. We are now able to see the atom, and these determinations, the determination of the radius has become possible nowadays. So when we talk of an individual atom, it is very difficult to determine its size because of this concept. And you know that according to Heisenberg's uncertainty principle, the position and momentum, momentum means the velocity at which the electron is moving, cannot be determined accurately. So the position of the electron is uncertain means the radius of an atom is difficult to be measured. So the atomic radius is measured in terms of three. It can be measured in three different ways. They are covalent radius, van der Waals radius, and metallic radius. What do you mean by covalent radius? So when an atom combines with another atom, let us talk of non-metals. I have given in example 1. I have given in example 1 here that when we are talking of non-metals like chlorine, it is not possible to take the atomic size of a single chlorine atom. But when two chlorine atoms combine together, they form a chlorine molecule. And the internuclear distance between the two atoms, if we draw like this is one chlorine, this is another chlorine. May not be symmetrical. So this is the nucleus of one chlorine atom. This is the nucleus of another chlorine atom. Just connect the 2 points, that is the nucleus, and half the distance of the internuclear distance, half, is its covalent radius. That is, covalent radius is measured in non-metallic elements when they form a compound, a molecule with their own atom, like chlorine, hydrogen, etc. So in case of chlorine, the total internuclear distance is 198 picometer, that is 10 to the power minus 12 meter, while half the distance is 99 picometer, which is the approximate atomic radii of one chlorine atom. Similarly, if we go to metallic radius, then we have to take 2 adjacent metal atoms in the metallic crystal. You might be knowing in a metallic crystal, the metal atoms are perfectly packed in order. So here, the internuclear distance, if we determine like this, and we take half the distance. Here there is overlapping. Here there is no overlapping. They are very close and adjacent. So obvious, the half of the distance between two metal atoms in a metallic crystal will be greater than the covalent crystal if they are of the same size, if the atoms are of the same size. For example, if we take a copper crystal, then with the internuclear distance between the two copper atoms is 256 picometer, and half of the internuclear distance is 128 picometer. So the metallic radii of copper atom is 128 picometer, whereas the atomic size of one chlorine atom is 99 picometer. That is in terms of covalent radii. And in case of noble gases, which do not combine with each other, when they do not combine, how to measure their atomic size? So we have to identify them like this. They are not bonded. So their internuclear distance is like this, and the two neighboring noble gas atoms, neighboring, non-bonded, they are in half of the internuclear distance, gives you the van der Waals radius. So three types of radius. If we go back, it is covalent radius, van der Waals radius, and metallic radius. Three things. So again, I repeat that covalent radius is measured for non-metallic elements. Van der Waals radius is mostly measured for noble gases, which do not combine with each other. And when we are talking of metallic crystals, we can determine their atomic size in terms of their metallic radius. But the mostly used atomic radius is the covalent radius. So, this atomic radii can be measured by X-ray analysis and through very powerful microscopes like SEM, scanning electron microscopy, or transmission electron microscopy. When we are talking of the atomic size, the atomic radius when we are talking of, we will discuss their variation. Let me come to this point. Let us watch the variation of atomic size along the period and down the group in case of S block elements and P block elements. When we talk of S block elements, that is group 1. In the previous notation, it was group 1A, and for group 2, it was 2A. For P block, the designations were 3A to 8A. You know that Sir has extensively discussed about all these things. So when we are talking of group 1A or group 1, excluding hydrogen, others are metals called the alkali metals. If we see the pictorial representation of their atomic radii, you see how the atomic radii increases down the group due to the addition of new quantum levels, new orbits, new cells. While the size of hydrogen is 37 picometer, you see the size of cesium with 7 cells, orbits, is around 265 picometer. So, atomic radii increases down the group due to the addition of new cells. And when we go across the period, then you see atomic radii, atomic size or radii gradually decreases with one exception in second period, that is in nitrogen. When you compare the atomic size of nitrogen and oxygen, fluorine, they are little bit higher in size than nitrogen. Some anomalies are there in between. Everything cannot be generalized in a general manner. There are some anomalies. We are discussing about the general properties, the general trend in properties of the metals. So when you move from lithium to neon, you see the atomic size generally decreases. I repeat, generally. Exception is with nitrogen. I have rounded it up. And that happens in all other periods also, with little bit exceptions at bismuth in 6th period, antimony in 6th period, and bismuth in 7th period. So, why this happens? Why the atomic size increases down the group and why the atomic size decreases along the period? We can discuss this with the help of two important factors, that is effective nuclear charge. In short, I can say ENC, and the shielding or the screening effect. What is effective nuclear charge? If we talk of a lithium atom, let us say a lithium atom. If I talk of a lithium atom, this is the nucleus. Let us say nucleus, first orbit and second orbit. Here there are 2 electrons, one s2, and there is another electron in the second orbit. So effective nuclear charge means let us say these are the electrons. So effective nuclear charge means there are 3 protons in lithium, 3 protons. So the 3 protons are attracting the 1s2 electrons as well as the 2s1 electron towards itself. Now, the attractive force experienced by the 2s1 electron by 3 positive charges is less than the attractive forces experienced by the 1s2 electrons because they are at a smaller distance and they screen the nucleus or shield the nucleus from the 2s1 electrons. Shield means they give a cover for which the nucleus cannot attract the 2s1 electron properly. And you know that the electrons are revolving at a tremendous speed around the nucleus. We cannot say there are 2 electrons in 1s2. Rather, we say an electron cloud is revolving around the nucleus. And the nucleus is busy for them. It cannot extend its total strength of attraction on the valence electron, that is the 2s1 electron. So 2s1 electron experiences less repulsion. This is called the screening effect. And we say shielding is effective when the orbitals in the inner shells are completely filled. You might be knowing that when we are going to transition elements, the inner orbital is not yet complete. The inner orbit is not yet complete. The d orbital is incomplete. Whereas the outermost orbit, that is the 4 in case of 3D series transition elements, the outer orbit is filled. So shielding effect is very effective when the orbitals in the inner cells are completely filled. In case of lithium, the inner cell is completely filled. That is 2 electrons in the first orbit. It is filled. So it exercises its shielding effect on the nucleus for which the nucleus cannot apply its total strength of attraction on the valence electron. Again, S electrons are more attracted towards the nucleus than the p electrons because S electrons are more oriented towards the nucleus. P electrons are less penetrating towards the nucleus. The penetrating power of the electron cloud is S greater than P greater than D greater than F. S electrons are more penetrating towards the nucleus than P, than D, than F. So, P electrons are shielded by the inner S electrons. Once shielded means, shielded word used means it is the inner orbit electrons. So, these 2 factors, effective nuclear charge, that is not the actual nuclear charge, it is effective nuclear charge. So, the nuclear charge which decreases with distance due to the shielding effect of the electrons in the inner orbit, they control, they regulate the atomic size variation in the periodic table. Let us say this is the point. So when we are going down in alkali metals, that is 1a, orbits are increasing 1 by 1. There are 7 orbits in cesium. So the nucleus is getting far inside and the valence electron is far outside. Therefore, the nucleus cannot exercise its full attraction on the valence electron so size increases. But while we are moving along the period, the electrons are added in the same orbit along a period. Let us say second period, the electrons are added in the same radial distance in the second orbit, while the number of protons increases in the nucleus. So the effective nuclear charge becomes more because the radial distance remains constant. So the nucleus exercises its full attraction on the valence electrons and the shielding effect is poor. So we can generalize down the group from top to bottom. Shielding effect is more due to the number of inner orbits and effective nuclear charge is less. So when effective nuclear charge is smaller than shielding effect, atomic radii increases, atomic size increases. But when effective nuclear charge becomes greater than the shielding effect, atomic size gradually decreases. So it is very clear from the data given in the diagram here in the slide where the measurements have been done in picometer units. Let us go to the next slide where the data of the elements with respect to their atomic size have been expressed in angstrom units. So when we are talking of angstrom units, that is picometer by 100 is equal to angstrom. Let us say this is 186 picometer, so it will be 1.86 angstrom units by 100. You can go like that. Then we'll go to the next one. So we covered that in case of normal elements, previously we discussed that in case of normal elements or representative elements, that is S block and P block, atomic size increases down the group from top to bottom and it decreases along the period from left to right because of the variation in effective nuclear charge and the shielding effect. But when we are coming to transition elements, that is the D block elements, generally we are considering only 3 series of elements, 3D series of transition elements, 4D series and 5D series. You know earlier that 3D series starts from scandium, ends with zinc, so 4D series is yttrium to cadmium and 5D series is from lanthanum to mercury. Now, when we are comparing their atomic size, a peculiar trend is observed. Just watch this slide where the 3D series is in green line. It is decreasing. Along the period, it is decreasing. And in the middle, almost in the middle, it is almost remaining same. And towards the end, it is increasing. So the variation is fast decreasing. This is scandium, titanium, vanadium, chromium, manganese. From manganese onwards, the decrease is very slow and here it becomes same and copper and zinc have higher atomic size than that of the previous ones, that is cobalt and nickel. Similarly, when we are going to the 4D series, you see almost the same trend is observed. Decreases, remains constant almost, and then increases. And when you are coming to 5D series, you see when it is 5D means there are 6 orbits. 4D series means 5 orbits. 3D means 4 orbits. So obviously this red line should be much beyond this, should be like this. But it is very close to 4D series. That is due to an effect called the lanthanide contraction, the detail of which will be discussed in other videos. This is not the discussion to be done here because we are celebrating periodic table day. We are emphasizing the importance of periodic table. When we talk of chemistry, the baseline is periodic table. And when we are talking of periodic table, it controls chemistry. Symbol, valency, formula, everything from where you start, that is periodic table. So this is a video, this is a class where we are emphasizing to remember the periodic table so that you enjoy chemistry. You enjoy it. And the details of discussions are beyond the scope of our discussion today. We want to just restrict our discussion to some general characteristics so that we enjoy, we identify, we love the elements, and we read their properties, how they are applied in different fields. When we are talking of the next slide, then atomic size is over, we are coming to ionic radii. What is an ion? An ion, it is, what I am discussing, I am not discussing only for class 12 or class 11 students. I am discussing for the class 9 students too. When I am talking of 9 students, class 9 students, they have no idea about the periodic table. What I think in CBSE syllabus, periodic table concept is not there. And I know that periodic table concept starts with class 11. But some idea has been given in class 9, and the periodic table is there in class 10 to some extent. Maybe, I am not sure about that. And class 11 it is there. So we are focusing on some of the physical properties. Let us come to ionic radii. When we are talking of ion, we are talking of a cation and one anion. A cation is formed from an atom by the loss of electron, one or more, and an anion is formed from an atom by the gain of one or more electrons. So when I am talking of two ions, it is cation and anion. Here I have written that the ionic radii can be estimated by measuring the distances between the cation and anion in ionic crystals. In all substances, we do not get ions. We get ions in ionic bonded compounds. So when a cation and anion, let us say sodium plus and Cl minus, this is an ionic solid. In ionic crystal, the distances between the cation and anion gives an idea about the ionic radii of that ionic crystal. Coming to cations, cationic size is always less than its neutral atom from which it is formed. Just compare, sodium cation is 95 picometer in size, while sodium atom in the gaseous state is 186 picometer. How we measured the atomic radii of sodium? Let us say metallic radii. I have already discussed, when two sodium atoms are in close proximity in the sodium crystal where only sodium atoms are present, we can measure their distance, internuclear distance, and half of it is 186 picometer. So when we are talking of sodium, its atomic number is 11. That is 2, 8, and 1. There are 3 orbits. When you remove one electron from it, one orbit is removed from the system and its size decreases significantly. 186 and 95. Imagine. So a cation is always smaller in size than its atom. Sodium plus is smaller in size than sodium. Potassium plus is smaller in size than potassium. Calcium 2 plus is smaller in size than calcium, and so on. And when we are talking of anion, it is always greater than its neutral atom. Just for comparison, the anion, the atomic size of fluorine is 64 picometer. How we measured it? Can you answer? How we determined the atomic radii of fluorine to be 64 picometer? That is from its covalent radius, because it is a non-metallic element. But when fluorine gains one electron, the number of electrons are 2 and 7. Total atomic number is 9. When it accepts one electron, it attains the configuration of the nearest inert gas. And fluorine is very much interested to attract one electron to become fluoride ion and to attain the noble gas configuration. It has tremendous interest to attract that electron. So when it attracts the electron, the size of the fluorine atom, it contains only 2 orbits and the nucleus is inside. And the second orbit is very smaller in size with 7 electrons, 2 and 7. But when the extra electron is added to this atom, electrons are negatively charged. The atom wants to be more stable by attaining the noble gas configuration, but these valence electrons are not interested to add this electron to them because there will be less space and more repulsion, and they are not interested for that. Electrons are not interested, but the nucleus is interested to attract it. So after much trial, the electron is added to the outermost orbit, and due to electronic repulsion among the electrons, the added electron and the electrons which were present earlier, the atomic size increases significantly. 136 and 64. Imagine, it is more than double the size due to the addition of only one electron. So our conclusion is that an anion is always bigger in size than its neutral atom from which it is formed. Similarly, chloride is bigger in size than chlorine, sulfide is bigger in size than sulfur, and so on. So if we go to the next slide, you can just compare how they are moving. You see, lithium in angstrom unit, the data has been given, and lithium plus, sodium, sodium plus, potassium, potassium plus, rubidium, rubidium plus, cesium, cesium plus. Just compare their atomic size. Significant reduction in atomic size, maybe in picometer unit, maybe in angstrom unit, there is significant reduction. Why this happens? Again, the effective nuclear charge comes into play. Let us say lithium, or let us come to potassium. In potassium, there were 4 cells or orbits. When we are talking of K plus, 1 electron is lost and there are 3 orbits. So if we compare both the cases, in the number of protons remains the same inside the nucleus. Potassium, there are 19 protons. Potassium plus, there are 19 protons. Here it is a neutral atom, so the number of electrons is 19. 19 protons, 19 electrons. Whereas in case of potassium plus, there are 19 protons, but 18 electrons. So the nuclear pool becomes more, for which the atomic size, the ionic size decreases. You can compare the size. In case of potassium, it is 2.02 angstrom potassium atom, whereas in case of potassium cation, it is 1.33 angstrom. Imagine how drastic reduction is there because of the increased nuclear charge on the electrons. And again, in potassium plus, the outermost orbit is completely filled. 2, 8, 8. Although the d electrons are 1t. Thereafter, d electron enters. And when we are comparing that of the anions, atomic radii and their anionic size, you can just compare you will get an information. You see fluorine 0.64 angstrom unit and fluoride 1.33 angstrom unit. More than double. Chlorine, chloride, bromine, bromide, iodine, iodide. Almost the size is increasing in a very heavy way. And in pictorial manner also, like cricket ball, it has been seen how you see the bromine atom and see the bromide ion. The size increase in size because of the electronic repulsion among the electrons in the valence shell. The shell is compact, more electrons are there. Nucleus in both the cases, number of protons in the nucleus is same. But in case of anion, since one electron is more, the number of electrons outweighs, dominates the number of protons. So, when number of electrons are more than the number of protons, there is an inter-electronic repulsion among the electrons, for which the size or ionic size increases. That is why there is an increase of size between the ions. So here I have just asked that there is a term that is isoelectronic species. What do you mean by isoelectronic species? When some atoms or ions contain the same number of electrons, isoelectronic means number of electrons remaining the same. Let us compare. I have given some examples. That is sulfide ion, S2 minus. So atomic number of sulfur is 16 and 2 electrons are added. Total is 18 electrons. Chlorine atomic number is 17, 1 electron is added, 18. Argon, noble gas, atomic number 18. Potassium, 19, but it's proton, it's cation. That is 19 minus 1 is equal to 18. Calcium atomic number 20, minus 2 electrons, that is equal to 18. So in all these cases, you see, in all these cases, number of electrons are 18. And if we compare their size, which factor is to be taken into account? When it is an anion, we have to concentrate, we have to focus, we have to give more importance to the inter-electronic repulsion. Whereas in case of cations, we have to concentrate on the increased nuclear charge. And in case of atom, it is neutral, number of protons is equal to number of electrons. So if number of protons is more than number of electrons, atomic size decreases. If number of ionic size decreases, and if there are more number of electrons, then ionic size increases. So can you compare the size of these 5 in decreasing order? Which will be the biggest and which will be the smallest in size? Maybe atom, maybe ion. We have to arrange them in order because they contain the same number of electrons. So if we concentrate on these points, Rudra Narayan Sahu, good evening. Very good evening, Rudra Narayan Sahu. And Dinabandhu Senapati is there. Very good evening, sir. I'm trying my best to give you some idea about these physical properties. So, coming to my point, when I'm talking of these 5, we have to answer them very fast. We have to answer them in a very little time. Arrange the atomic or ionic size in the decreasing order of their radii. So which will be the biggest in size? So already we know that sulfur contains more electrons. So sulfide will be bigger in size than chloride. Then chloride will be bigger in size than argon. Then argon will be bigger in size than potassium. and potassium will be bigger in size than calcium 2 plus. I hope you agree with me or not. Anil sir, namaskar sir. So when we compare their sizes, just in the bottom point I have written, compare the sizes of these things in decreasing order. I have already told the answer that it is the anion is biggest in size and the cation with the highest magnitude of charge is smallest in size. So anion with a higher magnitude of negative charge is bigger than others, while the smallest size is with the cation with the higher magnitude of positive charge. So you can arrange them similarly. Only this is the point which I discussed, that is only true in case of isoelectronic species. Then we'll come to the next one. The first physical property and its variation we have discussed in detail. That is atomic size and ionic size. Again, I wish to summarize. In case of atomic size, two factors control the variation in size. That is effective nuclear charge and the shielding effect. And in case of ionic size, the factor which controls the size of the cation or the anion is the number of protons and the number of electrons present in the ion. If number of protons are more than the number of electrons, then ionic size decreases. And if the number of electrons are more than the number of protons, then there is repulsion among the added electrons and the ionic size increases. That is the point. Then we'll come to the next physical property, that is ionization energy or ionization enthalpy. Let me explain the term, what is ionization energy? These things are obviously difficult for class 9 and 10 students to understand, little bit difficult, but now the students are so much enthusiastic. Now the students are so much charged that they can easily understand the basic concepts of this discussion. We will only concentrate on 4 or 5 or 6 physical properties in this discussion. But let us go thoroughly. And my request will be, students who have understood the concept of atomic size and ionic size variation, they can go for some more examples and to find out the decreasing order and increasing order. I wish to remind you that the order is very important. What has been asked to be found out, that is, arrange the size of the atoms or ions in increasing order or decreasing order. That is to be more concentrated. Otherwise, the answer may be wrong. So don't be too fast initially. But once you understand the concept, your speed will increase definitely and you can answer any question. But always remember, there are some anomalies. We cannot do away with it. Everything does not go in a regular manner. Few exceptions will be there. It is better not to go deep into the logic, because the atomic size and ionic size are determined with very sophisticated instrumental facilities, and that data is accurate. After getting the data, we are generalizing it that this might be happening. This is the reason, this is the cause why this happens. So always remember, theory is not fast, experiment is fast. From experiments, logical reasoning is drawn. So after measuring, when we are talking of this 0.64 angstrom unit, This was first determined using technique F minus, that is fluoride ion, 1.33 angstrom units. That was determined using advanced techniques, and then logic was developed. Why this happens? Why an anion is always bigger than its neutral atom, and why a cation is always smaller than its neutral atom? Then the factors proposed were effective nuclear charge, interelectronic repulsion, shielding effect. So first understand the logic behind the concept, then apply. One or two elements may not grow properly. Some anomalous behavior, some controversial behavior may be there. But let us not be disturbed, perturbed by these things. We will only concentrate on the logic behind these variations. Next. When we are talking of ionization energy, it means the amount of energy required to remove, to knock out, to drag the outermost loosely bound electron from an isolated gaseous atom. So focus on these points, very, very important. Let us say the amount of energy. Energy means we have to express in a definite unit. In SI, it is kilojoule per mole. Required to knock out, remove. Knockout means remove the outermost loosely bound electron. Why this term has been used? Because already I have discussed that the electron which is present in the outermost orbit is away from the nucleus. It is not properly taken care of by the nucleus due to shielding effect exercised by the electrons in the inner orbits. So it is very easy to remove the electron from the outermost orbit. It is very difficult to remove the electron from the inner orbit because they are under the control of the nucleus. So the amount of energy required to knock out, remove the loosely bound electron from an isolated, and the atom must be in the gaseous state. If I say sodium metal bracket Am, ionization energy, then the question is wrong. It should be sodium gas. You have to convert the solid metal into gaseous form. You have to take a single isolated atom and remove its 281, the last electron from its outermost orbit. The energy required, the energy necessary to remove that electron. Why energy is necessary? Because the nucleus has a pull on the valence electrons. So you have to apply the same energy or little more than that. The same energy or a little more than that to drag out that electron. There will be a fight between the nucleus and the electron, and you with the electron. And sodium, not coming to sodium, then I am coming to the ionization energy. When you are removing only one electron from the outermost orbit, the energy required for it is called the ionization energy or ionization enthalpy, or symbolically IE1, and so on. Why so on has been written? Suppose take the case of sodium. It has got 281, only one electron in the outermost orbit. When we are talking of magnesium, there are 282. Two electrons are to be removed to convert it into the nearest noble gas configuration. Because magnesium will be interested to lose it. But I wish to repeat, I wish to remind, give importance that you cannot remove two electrons at the same time. Impossible. You have to remove electrons one by one. First you remove one electron, then the second electron, and if necessary, then the third electron. In case of aluminium, it is 2, 8, and 3. But Which factor is controlling here? You again come to effective nuclear charge, number of protons, number of electrons, concentrate on it. In case of sodium, there is only one electron. So after the removal of this electron, you have 11 protons and 10 electrons. So the nuclear pool is more, so size decreases and it becomes 10 electrons, means it attains the configuration of neon, the noble gas. Therefore, you have taken one atom in the gaseous state, you have applied IE1, it loses one electron, and you are getting a cation. So what is ionization energy? We can define. It is the energy needed, supplied, provided to a gaseous atom to remove the most loosely bound electron from its outermost orbit to form a unipositive cation. Unipositive cation, one positive charge, is called the ionization energy. Now you tell me that ionization energy is an exothermic process or an endothermic process. When we are talking of an exothermic process, let me do here. 1 minute. Let me do this again. Erase this data. So that the screen is a little bit clear, we can explain it again. This is a big chance for me because I am not supposed to discuss it here. Sir invited me that you come over to Uranium office and let us celebrate the day together. You will wear a T-shirt containing the printed with the periodic table. I feel very happy, very, very happy. You just cannot believe when I wear this T-shirt, and it is of very good quality. And this mug, Sarah's told me that you will be provided with, you will be given a gift, a mug. So I'm very happy today. Now, coming to the topic, if I say, when we remove, let us come to magnesium. Magnesium has 2-8-2 configuration. Magnesium, let us say it is in the gaseous state. Magnesium is a solid. It is to be heated. It becomes a liquid. It is to be heated further. It becomes a gas. Then we have to take one atom, isolated gaseous atom, one atom, and apply energy to form the unipositive ion. Remove one electron. You are getting magnesium plus gas. And now magnesium is 281. Earlier it was very stable. Now it becomes unstable. It wants 2-8 configuration. So we have to remove another electron, but it is not that easy. Because here there are 11 protons, 12 protons, and 11 electrons, because its atomic number is 12. So nuclear charge is very high. You are removing, this is 12 protons. You are removing one electron from a cation, not a neutral gaseous atom. So the nuclear pool has increased. The nuclear attraction has increased in the unipositive ion. So the removal of the second electron is not that easy, because you are removing the electron from the core of a cation. Here the electron is removed from the core of a gaseous atom, where number of protons is equal to number of electrons. Here the number of protons is greater than the number of electrons. Therefore, it is very difficult, it will be relatively difficult to get the magnesium 2 plus ion from magnesium plus ion. Magnesium plus will be happy to lose that electron to become magnesium 2 plus and attains the noble gas configuration of neon. But one should not be too happy because the process of removal of the electron is difficult. However, this operates, and you imagine this is the first ionization energy, IE1, whereas this is the second ionization energy that is represented as IE2. Obviously, IE2 will be higher in magnitude than IE1. And if we similarly consider aluminium 3 plus from aluminium, let me write it here, aluminium gas, aluminium plus gas, aluminium 2 plus gas, aluminium 3 plus gas. So this is IE1, this is IE2, and this is IE3. Now here this is a di-positive aluminium cation, means 13 protons, 11 electrons. So the nuclear power, the nuclear pool is very high, and to remove the third electron becomes more difficult, and IE3 becomes more than IE2, which is higher than IE1. You might be thinking, is it possible to remove the fourth electron, let us say carbon or silicon? Carbon 2, 4. If we go on applying energy to the atom in the gaseous state, we can remove the electrons one by one. So can we reach fourth ionization energy? We can reach, because you have to apply sufficient energy and electron will come out. But what will happen to the atom? What will happen to the atom in that state? When you are applying huge amount of energy, it is going to the ionic state. And when very high ionization energy is applied, it goes to the plasma state, becomes a highly unstable. So usually we discuss these three ionization energies, IE1, IE2, and IE3, and that is called successive ionization energy. My point is that from aluminium, you cannot remove 3 electrons at a time. Impossible. You have to remove the electron one by one. So these 3 terms are called the successive ionization energy. However, our focus in this discussion will be on first ionization energy only. You understood what is second ionization energy and third ionization energy? Each time you are removing an electron from the core of a positively charged ion, when it is IE2 or IE3, so it is becoming difficult to remove it. I hope you understood. Coming to the next one, what is the trend? Let us not discuss more on second and third ionization energy. Let us discuss on only first ionization energy, where we are converting a gaseous atom, isolated gaseous atom, single gaseous atom, to a unique positive cation in the gaseous state. So what happens here? So fast ionization energy increases across a period. Now you very well understood. If you keep in mind 3 terms, repeatedly I am telling, effective nuclear charge. First one is actual nuclear charge, effective nuclear charge, shielding or screening effect, and inter-electronic repulsion. If you only understand these 4 points, you can apply the concept of variation of physical properties. You can explain the variation in physical properties in a very nice manner. No problem will be there. Just concentrate on this. IE1, here it is written, IE1 increases across a period and decreases along the group. Instead of across, let me write along. Down the period, and we will write along the group. And it is down the period. Sorry, the reverse one. This is across a period, correct, and down the group. In the normal elements, that is the main group elements of S and P blocks, with some anomalies at group 2 and 15. We will come to that. So, point is that ionization energy increases along a period, along by across a period. Why? Already we have seen that, see, along a period, if we move like this, you see what happens to the atomic size, decreases. Nucleus is there everywhere, containing the same number of protons, but the size becomes smaller. When size is smaller, nucleus has tremendous control on the valence electron, on the electrons in the outermost orbit. So it is very difficult to remove the electron. Therefore, along the period, effective nuclear charge increases, atomic size decreases, so fast ionization energy increases. But while we are going down the group, what happens? Shielding effect increases. Shielding effect increases means the last electron remains away from the control of the nucleus. Let us say in case of cesium, the last electron is present in the 7th orbit, and the electron in the 7th orbit is being separated from the nucleus by 6 inner orbits. 1, 2, 3, 4, 5, 6. Tremendous shielding effect. The nucleus is unable to see the last electron. So is it not easy to remove that electron from cesium very easily? So while we are moving down the group, ionization energy decreases, means you require less energy to remove the electron in the valence shell than along a period, across a period, where it is very difficult to remove an electron from the valence shell of an atom along the group, across the group, across the period. So let us come to the data. See, from the table, the data has been given in kilojoules per mole. Ionization energy, only fast ionization energy. Just concentrate here that from lithium to beryllium, that from, if we go like this, just 1 minute. When we are moving from second period, you think of the second period. While we are moving from lithium to neon, see the values. 520.2. Once you come to beryllium, the next element, almost 900 kilojoule per mole. This is 520, this is 900. Imagine how difficult it becomes to remove a single electron from the outermost orbit of a gaseous atom. But while coming to boron, just compare these two, beryllium and boron. In beryllium, the last electron is the electronic configuration is 2s2. While in case of boron, the electronic configuration is 2s2 to p1. So in which case, screening effect is more. Here, Sir might have taught you in the earlier discussion, the first session, that if an electronic configuration is stable, that is fully filled and half-filled orbitals, then the atom is very stable. And it is difficult to remove an electron from a stable gaseous atom. Today now I have discussed with you that the penetration of electron cloud S is greater than P is greater than D greater than F. That means S electrons are more closer to the nucleus than the P electrons. Again, P electrons are more shielded by the S electrons in the inner orbits. So when we are concentrating on beryllium and boron, which electron can be removed very easily? That is 2p1 electron or 1 electron from 2s2. It is 2p1. So see, the fast ionization energy of boron is only 800 kilojoule per mole, where it is almost 900 kilojoule per mole. So this is a very important concept. Just I am cleaning it. You can see again, you see, it is 899.4, it is 800.6. But immediately come to the next one. See, there is a tremendous rise of about 286.4. Again rise, again less, again rises, and think of the noble gases. When you compare the fast ionization energy, you see the noble gases have the highest fast ionization energy. Highest. Why? Because they are very, very stable. So, they are not interested to lose their electron. They are therefore called inert gases, rare gases, noble gases, because of their very stable configuration. Now, so fast ionization energy, when we are comparing down the group, you see hydrogen, lithium, sodium, potassium, rubidium and cesium. What happens to the atomic size? Beryllium to radium, you see. What happens? Beryllium to barium, you see. What happens to the atomic size? It increases. When atomic size increases, the atom becomes bigger and bigger. It is very easy to remove the valence electron. So, fast ionization energy decreases down the group. So, what is the summary? Fast ionization energy along the period increases with one or two anomaly. Stable electronic configuration, atomic size, more effective nuclear charge, all these factors are coming into play. So, we are getting this value. Now, if we compare in a pictorial, in a graphical manner, you see atomic number and fast ionization is kilojoule per mole. You see what is the highest ionization energy, fast ionization energy we found in noble gases, and which elements in the periodic table possess the lowest ionization energy. That is the alkali metals. Just compare. Alkali metals have the least ionization energy and the noble gases have the highest ionization energy. So it is very clear that this is the observation. Next. While coming to this, you see me. So the first point you read again. Ionization energy increases across a period and decreases across the groups in normal elements. Metals have lower ionization energy values and hence form positive ions easily. Metals form cations easily because they have lower ionization energy. In transition series, in D block elements, fast ionization energy increases, but it is inconsistent. It is not regular. It is irregular. We may not go to the detailed discussion, but let us see the variations only. In transition groups, Fast ionization energy is highest in third element down each group. In some groups, increase down the group, that is vanadium, chromium, and nickel groups, and in all other groups, it decreases fast and then increases. I am showing you the graphs very shortly. My question is, if we compare boron and beryllium, just I was discussing boron and beryllium, tell me, boron and beryllium, when I am coming to this, just tell me which will be having higher ionization energy and why. You see, beryllium has, beryllium, ionization energy data is not here, it is atomic size. Beryllium is bigger in size, but its fast ionization energy is more. See, fast ionization energy of beryllium is more than boron. Already I have explained. Due to stable electronic configuration, penetration of s electrons towards the nucleus more. Here, the electron is present in 2p orbital, which is away from the nucleus, which penetration is less. Therefore, it can be removed easily. Now, that is the growth. Coming to fast ionization energy, which is expressed in kilojoules per mole, one example we will be giving. Again, this data has been assimilated at one place. You see, this is again the same data. This is beryllium and this is boron. Decreases, but in case of carbon, it again increases. Then we will come to the transition metals that I was discussing now. You see, when we are talking of fast ionization energy of transition metals, that is 3D series, (4D series, and 5D series. 3D series, 4D series, and 5D series. Think it. 3D series, 4D and 5D series. 3D is orange colored line. You see, what is the variation in ionization energy? Completely inconsistent, irregular. So we cannot draw a conclusion, a general trend properly. The same type of trend is observed in case of 4D and in case of 5D. But always remember, along the period, atomic size increases or decreases. Along the period, from left to right, across the period, atomic size decreases. Atom becomes smaller in size. Once the atom becomes smaller in size, it is difficult to remove the valence electron or single electron from its outermost orbit. So the general trend is increasing or not in all cases. A general trend, not specific, it is increasing, but irregularly increasing. Now, that data has been compiled in a graphical manner where you can see that the fast ionization enthalpy here, the fast ionization energy, here it is expressed in electron volt unit. You can express in kilojoule per mole, or you can express in electron volt unit. In this data, it is also consistent with the kilojoule per mole data that alkali metals have the least fast ionization energy, while noble gases have the highest fast ionization energy. We have already discussed about that. Next. The next property comes, that is electron gain enthalpy. What is electron gain enthalpy? Just the opposite of ionization enthalpy. Ionization energy or ionization enthalpy is an endothermic change. You have to supply heat to the atom to remove the electron. The just opposite concept is electron gain energy. It is written as Eg delta H Eg. Delta H is written in thermodynamics as heat change or enthalpy change. Just write electron gain. So what is electron gain enthalpy? Opposite of ionization energy. That is, the enthalpy change accompanying the process of addition of an electron. Here an electron is added, not removed, to a neutral gaseous atom. Neutral gaseous to A. A means it is again isolated. One gaseous atom is called enthalpy, electron gain enthalpy. When we are talking of a neutral gaseous atom, you can extend it to 1 mole of neutral gaseous atoms because the energy is expressed in kilojoules per mole. 1 mole of atoms. The value what has been given, that is for 1 mole of atoms. But in while we are defining a single atom. That is called delta H. Always remember, delta H Eg, enthalpy. If it is negative, then heat is released, energy is released. And if it is positive, then energy is absorbed. So you can imagine, in case of ionization energy, enthalpy change, not Eg, only enthalpy change was observed. That is positive sign. In chemistry, delta H is positive, means it is an endothermic change. And if delta H is negative, it is an exothermic change. So ionization energy was an endothermic change, while electron gain enthalpy is an exothermic change, because it is the change accompanying, means it is the amount of energy released mostly. But here you see delta H Eg, electron gain enthalpy, can be positive also in few cases. I will show you in next slide. For group 17, that is the halogens, they have the highest enthalpy gain, negative atoms, because they have a tremendous interest, attraction for the electron, because they will attain the noble gas configuration. But while we are talking of noble gases or inert gases, they have no interest for 1 electron. I will give 1 electron to neon. It is 2, 8. I will add 1 electron to neon atom in the gaseous state. It has no interest at all. It will not look at the electron. But you are interested to push that electron into the neon atom. You can forcibly push it. You have to supply energy to forcibly put it. It will never show any interest to attract that electron. That's why in case of noble gases and 3 atoms, few atoms, delta Eg, delta H Eg is positive. So always remember, ionization enthalpy is always endo, while electron gain enthalpy, delta H Eg, may be positive, may be negative. So if we are coming to the next slide, it is electron affinity. Always remember, electron affinity and electron gain enthalpy are same. Approach is same, but their dimension is totally opposite. So what I have told in electron gain enthalpy, it is the amount, if an atom is interested to attract 1 electron, it will utilize its energy to attract the electron. It is doing some work, so it will be losing some energy. If an atom is not interested for an electron, but we are forcibly interested to push it in, we have to supply energy. But on the other hand, what is electron affinity? It is the affinity for an electron, and it is the amount of energy liberated by a neutral isolated gaseous atom to accept an electron to form uninegative ion. An atom accepts 1 electron, means, let us say, X gas plus electron gives you X minus gas. uninegative ion. Those which do not liberate energy, while an electron is added, then we assume their electron affinity value is 0. In fact, they have negative electron affinity values. No interest. Means electron affinity and electron gain enthalpy are the same terms, but their magnitude dimension is different. In electron gain enthalpy, we express the energy in terms of delta H. Here the energy is expressed in terms of exo change. Always energy is released. But if somebody is not interested to attract the electron, its electron affinity is accepted to be 0. So here, non-metals have greater electron affinity values from negative ions easily. That is X, that is halogen. Halogens are generally represented as X. Fluorine, chlorine, like that. If an electron is added, it forms X minus gas atom with the release of energy because it has interest. But suppose I will say nitrogen 2, 5. When we are adding one electron to it, nitrogen gas, it will not show any interest. I will show you in the graph. So, electron affinity is defined, electron affinity term is defined at absolute 0. But electron gain enthalpy can be used at any condition. So, it is better to use electron gain enthalpy in comparison to electron affinity. And both are related like this. Electron gain enthalpy is equal to minus of electron affinity value minus 5/2 RT, where T is the Kelvin temperature and R is the universal gas constant. Now, coming to the next slide, the values of electron affinities are given here. Let us not concentrate on that. These are the same things and this has been expressed. Again, I just summarize what is ionization energy, what is electron affinity. Ionization energy is the process of removing an electron from the outermost orbit of a neutral gaseous atom to form a unipositive cation. While electron affinity is the amount of energy released, XO, when one electron is added to the outermost orbit of a neutral gaseous atom. If we compare the values you see, very important point is that you concentrate on these 2-3 points. See. Compare fluorine, chlorine, bromine, iodine, group 17. What happens to the electron affinity value? Decreases or increases? Decreases. That means fluorine has tremendous affinity for an electron to become fluoride ion. In comparison to that, chlorine has less. Oxygen, sulfur, nitrogen, phosphorus, carbon, silicon, boron, aluminum. In the P block, you see, they have interest for the added electron. So, more amount of energy is released to drag that electron. But down the group, it decreases, means iodine has less attention for the electron because iodine is bigger in size. Nucleus is, who is attracting the electron? The nucleus or the center. So once the atom becomes bigger in size, the nucleus is far away inside, it has least interest for the added electron. So less amount of energy. So will be released in case of, because iodine is not paying any interest for the added electron. So less amount of energy is released. But when we are coming to another important term, that is electronegativity. Just another 1 or 2 physical properties I will summarize at the end. Electronegativity means it is the relative tendency of an element to attract a shared pair of electrons in a covalent bond. So always remember, Ionization energy and electron affinity are applicable to isolated gaseous atoms. But electronegativity is related to the power of attraction of an atom for a shared pair of electrons. Means two atoms are already bonded. Covalent bond means two electrons have been shared at the middle. The two atoms may be same, may be different. If the two atoms are same, they have equal attraction for the shared pair of electrons. But if the two atoms are not same, then one is powerful, the other is weak. Then the powerful element attracts the shared pair electron towards itself and becomes slightly negative, while the weak atom becomes slightly positive, leading to the development of polarity in the molecule, delta plus, delta minus. I am talking of this, you will see. Suppose I am talking of H, shared pair of electron. Both are same. So they have same force of attraction for the shared pair of electron. Cl, same. But when we are talking of HF, shared pair, already we have discussed about we are discussing about electronegativity. Fluorine has a tremendous attraction for the shared pair of electron. Once it takes the pair of electron, it becomes delta minus and hydrogen becomes delta plus. So this is the development of polarity, and that covalent bond becomes polar. So if somebody asks, what is the nature of a covalent bond? Is it always polar or it is non-polar? We measure the polarity of a covalent bond in terms of electronegativity values. And the term here utilized is DEN, that is difference in electronegativity value. And for that, you have to remember this point, very important. The electronegativity value have been measured for fluorine, all elements. Electronegativity values have been measured, and it is clearly written in the periodic table. In the MOG, we have printed. And they can be measured in three different scales. One is Pauling scale, one is Mulliken-Jaffe scale, one is Allred-Rocco scale. But the most popular is Pauling scale, where the values of the elements have been, the electronegativity values of the elements have been found out or calculated. Always remember, which element in the periodic table has the highest electronegativity value? That is fluorine, that is 4. The second most electronegative element is oxygen. Then nitrogen and chlorine have 3. Bromine is 2.1. Carbon is 2.5. Hydrogen is carbon, has 2.5 Pauling scale, and hydrogen is equal to 2.1. This will help you a lot in organic chemistry, because organic compounds are connected to each other by covalent bonds. So the point whether a covalent bond is polar or non-polar can be decided on the basis of electronegativity value of the atoms. So if the difference in electronegativity is 0, come to this point, is 0, if the electronegativity difference between two values, between two atoms is 0, difference in electronegativity, that means both the atoms have the same electronegativity, then that covalent bond is non-polar. But if the this is chlorine, hydrogen, their difference in electronegativity is 0. So they are non-polar. But when we are talking of HF, HCl, HBr, HF, HCl, HBr, there is difference in electronegativity value. How much? Fluorine and hydrogen is 2.1. 2.1. So imagine the electronegativity difference. 4 minus 2.1 is 1.9 between hydrogen and fluorine. So this is negative pole, this is positive pole, and this covalent bond is a polar covalent. Always we measure the electronegativity in Pauling scale. That is the popular scale in which we are measuring. Again, we have written metals have lower value of electronegativity because metals are interested to form positive ions. They are not interested to form negative ions. They have no interest, least interest for a shared pair of electrons. But non-metals have higher electronegativity values because they're interested to form anions. Metals are interested to form cations by losing electron. Non-metals are interested to attract electron to form anions. So, electronegativity of metals is less than 2.2, while in general, electronegativity of non-metals is more than 2.2. And the most important generalization is that if the difference in electronegativity is greater than 1.7, difference, just I have given you the example, difference of electronegativity between hydrogen and fluorine in HF, hydrogen fluoride, is 1.9. If it is greater than 1.7, the bond is predominantly ionic. So it is a covalent bond with more ionic character. Although don't take that it is 100% covalent. Electronegativity difference greater than 1.7 implies it has a greater magnitude of ionic character. And if the difference in electronegativity is less than 1.7, then we say it has predominantly covalent character. So a covalent bond has some ionic character and covalent character. How much ionic and how much covalent, this depends upon these two values. If DEN is more than 1.7, it is predominantly ionic, and if it is less than 1.7, it is predominantly covalent. Along the period, electronegativity increases. Why? Because along the period we are proceeding, we are moving towards non-metals, which are interested for electrons to attain noble gas configuration, to form anions. While down the group, as the size increases, they have least interest for an electron, a shared pair of electron, for which their electronegativity value decreases. I hope you understand the logic. So much discussions in a limited time, it is difficult. You know, these properties with all examples, many examples we can take. It will take a lot of time to do. So if you understand the concept, you please apply. You take some examples, some questions, and apply this concept. This is available to you in the screen. This is available to you in the YouTube. Then only you can love it. So electronegativity is in Pauling scale, you see. This is a very important concept. Just some few slides are there. I hope I am moving in a little speedier way. But I feel that only if we discuss the summary, the definitions, the exact concept behind all these things, only 4 things we are discussing. Atomic size, ionic size, ionization enthalpy, that is only first ionization enthalpy, electron affinity or electron gain enthalpy, and electronegativity. Only 5 physical parameters. Then this one is very important. You see, what happens? Compare fluorine and chlorine, electronegativity, oxygen and sulfur, nitrogen and phosphorus, electronegativity decreases down the series, down the group. But coming to electron affinity, that point is very, very important. See, electron affinity, you see the electron affinity of nitrogen is a dot only, that is 0, because it has a stable configuration, half-filled electronic configuration. It has no interest for an added electron. But think of these 3 pairs, very important. I want to highlight. Electron affinity, I am telling. You see, electron affinity of all the noble gases is almost zero because they have no interest for an electron. For an electron, because we are talking of isolated gaseous atom. But when you compare these two pairs, always remember, see, fluorine and chlorine, which has a higher value. Electron affinity should decrease down the group. But when we are comparing fluorine and chlorine, chlorine has a higher electron affinity than fluorine. Sulfur has a higher electron affinity than oxygen. Phosphorus has a higher electron affinity than nitrogen. Silicon has a higher electron affinity than carbon, and aluminum has a higher than boron. But gradually you see this is decreasing. So from this third period, it is like this. The data is like this. But why in the second and third period we are comparing, the element in the third period has a higher electron affinity than the element in the second period. Second period is smaller in size, small atom. Third period, second period is smaller, third is bigger. So which element, second or third, which should have higher electron affinity? Electron affinity means nucleus is nearer. So this should be having higher electron affinity, smaller one, and the larger one should have smaller affinity. But the reverse is true here. Because when an electron is added to a small orbit, there is electronic repulsion. That is why, always remember this one point, that chlorine is more than fluorine in electronegativity. In electron affinity, chlorine, but fluorine is greater than chlorine in electronegativity. The same is true for sulfur and oxygen. Oxygen has more electronegativity than sulfur, but oxygen has less electron affinity than sulfur. See, nitrogen has more electronegativity, right? I have written 3.0 Pauling scale than phosphorus, whereas nitrogen is less than phosphorus in electron affinity. Always remember electron affinity and electronegativity relationship in between these two elements, these three sets. That will play a very important role, that will help you a lot in the long run. Then the final one is almost final one, that is the melting point and boiling point. You know, melting point is that the temperature at which a solid is converted to a liquid. In a very general sense, I am telling, a solid is converted to a liquid. And boiling point, a liquid is converted to its vapors, changes to its vapor or gaseous state. It is measured in temperature. So, if we compare the variation in a period, across a period, melting point increases up to certain element and then decreases, and down the group, it shows inconsistent patterns. So, you should not be serious about that. Only let us concentrate on few groups. In alkali metals, melting point decreases down the group. Why? Because down the group, size increases gradually. So, the melting point decreases. And in case of group 2 metals, they have higher melting point than group 1 because along the period, atomic size decreases. So, smaller the size of the atom, higher is the melting point. Bigger the size of the atom, lower is the melting point. And in case of P block, you see, in case of P block elements, when we are concentrating on P block, diamond has the highest melting point, 4000 degrees Celsius among the elements, while gallium is the lowest melting point metal, having 30 degrees Celsius, means it is a liquid at room temperature almost. We are not focusing on transition elements. This is about D block elements. Only one point I want to focus, that you see in the transition elements, which have the highest melting points. See, which transition metal has the highest melting point? That is tungsten of 5D series, molybdenum of 4D series, and chromium of 3D series. They are having the highest peak of the curve. So remember this, it will help you. And finally, that is the density. At standard states, that is room temperature and atmospheric pressure, gases have the lowest density in comparison to the solids and the liquids. While in a period, it increases up to certain element and then decreases, and in a group, it increases with some irregularities. Inconsistent variation is there. And remember this one, that in osmium point, not to be very serious about it, some data is there. Osmium is greater than iridium at 1 atmospheric pressure density. But once pressure becomes high, iridium is having more density than osmium. It is a pressure parameter which also decides the variation in density. So these values are highlighted here in osmium and iridium in the table. Then coming to the chemical properties, I am not interested to discuss a lot about chemical properties. My focus is on physical properties, physical parameters that we have discussed, and I want to ignore that, but I will definitely wish to discuss about the oxidation states in the groups, because oxidation state is very important in deciding the nature of the metals while they are going for bonding. Alkali metals in general, all the metals have only one oxidation state, that is +1. Oxidation state is always expressed in terms of a charge, either positive or negative or zero. It can be a fraction also. So always remember, alkali metals have oxidation state +1. Alkaline earth metals have +2. That is group 2 elements, group 1 elements. I am talking of metals. There is a non-metal. You know the position of hydrogen is very controversial in the periodic table. So take it as alkali metals, group 1 +1, group 2 +2, group 13, just deduct 10, that is +3 in general. But the last element in the list in group 13, that is thallium, it shows +1 oxidation state. Group 14 -10, general oxidation state is +4, and when it behaves as a non-metal, it loses 4 electrons. It becomes +4. When it gains 4 electrons to attain the noble gas configuration, it becomes -4. So the first one has been given the highest oxidation state, and the second data has been given as the lowest oxidation state. This series is the highest oxidation state exercised by the elements, whereas the second data, this one, is the lowest oxidation state possible. Others are variable oxidation states are possible in some elements. Now, this has been pictorially in a graphical manner, in a tabular manner, the data has been given, and the oxidation states have been given in a systematic manner for the elements of transition metals. So, my point of discussion was today, why we are reading these properties in the periodic table and their variations, because they decide the chemical nature, the nature of bonding, the forces of attraction with other atoms, formation of compounds. All these factors play a very important role. And today we discussed about which factors? Size, that is size, 2 atomic and ionic, then ionization enthalpy, then electron gain enthalpy or electron affinity, then electronegativity. then oxidation state, and somewhere a little bit about density. Not to be serious about it, just go through your materials, study them. You will only understand them perfectly if you do some exercises. And I am interested to give you some exercises within a very short period. Within a very short time, I had to discuss that. So I wish that I should give a slide and I can write some questions. If you are ready to answer, you can do that. Number one. Number one, you see, I am interested to do that. Which has lower ionization energy, chlorine or fluorine? IE, IE1, lower. Which has lower, chlorine or fluorine? While we are moving down the group, atomic size increases. So ionization energy decreases. Therefore, chlorine has the lower ionization energy. And when we are talking of nitrogen and oxygen, in which case delta H Eg, electron gain enthalpy, will be more. Just have an idea. Nitrogen and oxygen, they are present across the period or down the group. Second period, they are across the period. What about the size? Decreases. So oxygen is smaller in size than nitrogen, in which case the nucleus is closer to the valence shell in oxygen. So if we add one electron, electron gain enthalpy means when we are adding an electron, the amount of energy released will be higher in oxygen than in nitrogen because it is bigger. It is relatively smaller. Nucleus is closer. So it has an attraction for the added electron. So in this case, delta H Eg will be higher, means more negative. That is very important. Delta H Eg is higher means it is more negative. Now, we can just another one example last we can conclude. Or I can add another slide here. And I can say another one. Which of the following has the smallest size? Let us say smallest size and largest size. Last question. That is Al3 plus Cl minus O2 minus Mg2 plus. Be quick. Smallest size. The atom with highest magnitude of positive charge is smallest in size, and an atom or ion with the highest magnitude of negative charge is largest in size. So this is largest and this is smallest. I hope you understand the concept, and it is difficult to discuss all these things in a very short period of time, but I hope you must have enjoyed the program, and you will enjoy it more when you go through your text and do a lot of exercises. In case of any doubt, you can interact with uranium later, and will be definitely there to clarify your doubts. Those students who are outside Cuttack and are interested to procure the periodic table mug, you can write us. If you are outside Cuttack, we'll be interested to send it to you in any form. But if you are actually interested for this mug to have it is like a memento from uranium, you can procure it. Of course, we are spending a lot of money and energy in preparing this. It is not a small task. It is a very difficult task. And Sir has tried a lot to do it. So if you are really interested to keep it on your study table and enjoy the periodic table, see the periodic table, which is the basis of chemistry, then you can write to us. And those who are off Cuttack, you can come down to uranium office at Friends Colony and collect your item from the office. We will be happy for it if you come over here. Thank you so much.
Hello and once again welcome. This is again Sudhansu Tripathy. We are signing out now, and tomorrow will be the last class to commemorate the 3 days celebration of the periodic table day, starting from 7th. Today is 8th, and tomorrow at 7 a.m. in the morning, I will see all of you to discuss very fascinating aspect of radioactivity and the synthesis of radioactive elements. And you can ask any doubts that you are having till now. We'll be interacting on a one-to-one basis tomorrow. Bye. Have a good night. See you tomorrow at 7 a.m. From all of us, Dr. Das and myself. Have a good night.